Turn on the. Because I have to turn it on and then turn it off after this, as usual. Okay. Pretty close to the time. Let's see, thanks. So, not yet. No yet. Oh, there's Burkhard. Let me promote him there. Join in a second. Hi, Burkhard.
Hello. Hello, Joerg.
Hello.
Okay, I think it's time. So I would like to welcome everybody once again to the online SPICE and SPIN+X seminar series that I lead here in Mainz with together with Libers Meckiel, Angela Wittmann, and Karin Hebeso now in Duisburg, and in collaboration with the SPIN+X Collaborative Research Center led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern and Matthias Chloe here in Mainz. As you all know, this is a webinar format, so you can only see the speaker at the moment, me, and the presentation itself. And yeah, and then, but please, you can write down the Q&A or in your answer, or raise your hand, and I will give you the floor to ask the speaker the questions during the Q&A time. Next week, of course, we have a DPG meeting, so there will not be no seminars, but please note that already Stuart Barkin will be joining us the week after that as well, and there's all this schedules during the next week. Today's is a long time friend and collaborator, Joerg Wunderlich, who is now a professor of experimental physics at Regensburg University after being a long time in Prague and Hitachi Cambridge as well. He started his education in France, of course he's German, and then he went to Halle, all over the place, very international, and was for a long time in Cambridge, where he did very important work in the spin discovering of the spin Hall effect in two-dimensional systems, and has been working on many aspects of physics of the spintronics. He has several awards like the Perky Fellowships, the IEEE IOP Wolfrath Prize Award, and the RCASD Fellowships at the University of Tokyo. So with this, and he always looks the same. It doesn't age a bit, which is very annoying, frankly. But other than that, I'll forgive him for that, maybe. So please go ahead and share your screen now, Joerg, and you can start your presentation whenever you like.
Hello. Thank you very much, Jairo. And
you have to share your screen.
I do. Okay.
Bit chaotic.
Yeah.
It's coming, not yet. Yeah, perfect. Thank you.
Sorry. Also, this hasn't changed over the years. I'm sorry. And thank you very much, Jairo, for this nice introduction. And thank you for all those who are spending their time on this afternoon to listening about some work we did about antiferromagnetic domain-borne memories and also antiferromagnetic oscillators. Both are driven with spin-orbit torque. And actually, the work I'm presenting, it should be not me, it should be those two people. First one is Pradeep Kumarut, who worked mainly on those oscillators. I'm presenting you his work. And the other one is João Godinho, who was PhD student in Prague and in Regensburg, and now he's became a postdoc. Pradeep is still a PhD student, and we couldn't have done all this work without the help of those multiple groups. One of them is the group of Christian Bach in Munich. Here, I would like to mention Franz Wilsmeyer, who helped a lot and did a lot with respect to optical detection methods like BLS, micro BLS, and also time-resolved polar mode measurements. All the materials I'm talking about today were grown by Ruslan. He's from the group of Olaf Hellwig, and he's from Dresden, from the Helmholtz Center in Dresden. And all the devices I show you the data from were fabricated by SPIN+X. He's from the group of Thomas Jungwirth in Prague. And Ruben helped a lot also with the theoretical description of our system, and is still helping. So this work is actually still ongoing. So maybe from this point of view, it's perhaps interesting to some of you. Okay, so the introduction, how to do it, how to motivate this. It's indeed this big topic of neuromorphic computing. So human brains seem to be very energy efficient, to do a lot of computational power, so 10 to the 18 flops for only 20 watts. Maybe not so perfect in many senses if you think about present and former dictators around, but still, if you compare this with powerful supercomputers, they can maybe do the same computing power, but they need about 1 million times more energy. And they are based on a Newman architecture, and they are static, whereas our brain is much more flexible. Well, we have oscillation, synchronization, and stochasticity. All this plays a big role. And the question is, can spintronics somehow help with this to mimic at least the function, the basic functionalities of the building blocks of neural networks? And what are those building blocks? Those are neurons and synapses. Whereas the synapses, if you put them in a kind of artificial neural network, those are a type of analog memories or memristors, multi-level. So you have to, in principle, store non-volatile, if possible, data in those synapses. And they should be flexible to be modified and to change their synaptic weight. And on the other hand, also you have neurons, which are in principle integrators. They integrate all the inputs they get from all the other neurons they're connected to. And if these inputs go over a certain threshold, then they trigger an output, and this output goes then to the next level of neurons. So on this basic, simple level, people try to build or even to simulate neuromorphic computing and neural networks. So how can do antiferromagnetic spintronics with it? Here I just wrote a couple of properties of antiferromagnetic spintronics. And I think two properties here are particularly important for the work we are doing. One is the fact that at least a compensated antiferromagnet, it doesn't generate stray fields because there's effectively no net moment. At least on a global scale, there is not really a net moment. And therefore, dipolar coupling, which is usually long range, is not playing a strong role. And as I show you, this can play in memories which are based on antiferromagnets a very important role, because you can write, if you can write them, if you can modify the magnetic order of such a system, you can do it very reproducible. Especially if you work at a temperature, at higher temperature, at room temperature, because of thermal fluctuation which act everywhere, and they would have then influenced also everywhere via the dipolar fields. They get actually, the effect get suppressed, and they average actually out. So you can also then think about long-lasting and robust storage if you be able to build memories based on antiferromagnets. And especially because you can you are so reproducible, you can also think about analog memories. You can have many multiple states, not only just 1 and 0. And the other thing is, of course, the very high dynamics antiferromagnets come with, the exchange field enhanced dynamics, which make, if you can make those oscillators, magnetic oscillators, out of antiferromagnets, they can be much, much faster. And the dynamic is also much more complex than a simple ferromagnetic oscillation. So that's also especially important for neuromorphic computing. So they can be fast, they can also be tunable. maybe more tunable than ferromagnetic systems, and the dynamics is more complex. Okay, so I will start. So my talk will be, in principle, contain two parts. The first part is on the multi-level memory, or kind of analog memories based on antiferromagnets. The second part is on the antiferromagnetic oscillators. Both of them, as I said, are driven by a spin orbit torque. Okay, so there is one early work, pioneering work, using actually antiferromagnets for kind of analog memory. It was done by Sunsuku Fukami. And so what he realized at the time was, in principle, a very simple system, an exchange biased ferromagnetic film, which is exchange biased to an antiferromagnetic film. And all this patterned in a Hall cross structure. You could measure the Hall response of this system. And since you had this interface between the cobalt nickel here and this ferromagnetic film and the platinum manganese as the antiferromagnetic film, at this interface, when you send a current, you get spin accumulation, and this can drive you a domain ball propagation or a reversal in this system. And since it's strongly exchange coupled to the antiferromagnet, when you have an imperfect reversal, imperfect means not a full reversal, so it's just a partial reversal, your domain pattern remains stored, and information comes somehow embedded into the domain configuration or the spin configuration of this platinum manganese. Despite you not really see it, what's happening there, but it stabilizes you the domain configuration of the ferromagnet as well, due to this strong exchange coupling between the two layers. Another work here, more recent, is only based on an antiferromagnetic system. And what's the key point here is that antiferromagnets, as ferromagnets, contain magnetic domains. And those domains, if you come to temperatures which are close to the transition temperature from a magnetically ordered system to a paramagnetic system, you can actually destroy them. You shatter them. Maybe you even go above the Néel temperature. And when cooling down, you generate very small antiferromagnetic domains. And those domains, on the local scale, they might be only a few tens of nanometers or so. They cause a lot of magnetic scattering, and so the device resistance changes. And as you can see here, if you use current pulses, the same works actually also with optical pulses, they effectively heat up your magnetic system, and then you destroy, you shatter those domains to small domains, and the device resistance changes. However, what you also see, those systems are not really non-volatile, because you get, and this is quite a complex process, a kind of clustering of these very small domains to bigger domains, and domain wall creeps and all these things play probably a role, and you get those kind of stretched exponential time dependency of the signals. So you can reproducibly write those structures, as you can see here in this graph, and sending pulses to heat up the system. But also you can also see, if you don't send pulses, then those signals decay again, and you will go back to the original macrodominic domain state. And then there's a special class of antiferromagnets. Those are antiferromagnets which have a combined symmetry, combined from the lattice and also from the magnetic order. Typical examples are manganese to gold, copper manganese arsenide. And well, what I will show you here, it's actually you can artificial antiferromagnetic systems, so-called synthetic antiferromagnet systems, and they all have a PT symmetry. And what does it mean, PT symmetry? P is the inversion, which is broken, for example, which might be broken entirely because of your magnetic order. And the time reversal, the T symmetry, is also broken because you have a magnetic system, which has always a broken time reversal symmetry. But you can combine them that both of these symmetries simultaneously are not broken. And I just show you on the copper manganese arsenide, if you have two sublattices, sublattice A and sublattice B, And if you apply the time reversal symmetry, obviously your spins are just inverting. They go to the opposite direction. So sublattice A and sublattice B orientation change by 180 degrees. But then you can do the parity operation. And you do now actually what you can see in this kind of spin structure. And you see this yellow point here. This is the inversion point. If you invert every atom from this point, you will actually reset that the sublattice A becomes sublattice B. And since you have changed already the spins from sublattice A to the spin to sublattice B, and now you reverse it via the parity transformation, you come back to your original system. Yeah? It has a PT symmetry. And what turns out in those systems which have a combined PT symmetry is that you can generate so-called staggered effective spin orbit fields. A bit imagine like a Rashba effect. So you have an electric field because of the local broken inversion symmetry, which is just opposite for your sublattice A and sublattice B. And then when you apply a global current for the whole crystal, what will happen is you generate effective spin polarization, if you want, a bit like a kind of a Rashba-Edelstein type of effect. But it's staggered. It's the opposite for the sublattice A and for the sublattice B. And if you send the current in the proper direction, this effective field corresponding then to the interaction between these polarized electrons and the exchange interaction and the local magnetic moments embedded in your crystal, they can give you a torque on the magnetic order, and you can actually, with this staggered effective field, you can actually generate a rotation of the magnetization. Well, this works in principle with this toy model, but it works also if you consider an antiferromagnetic domain wall with such a staggered field. You indeed can excite a domain wall propagation to such a structure. And our system, or our antiferromagnetic memory, which I would like to show you the results on it, is actually based on exactly such a type of torque. This is for writing, but you may also are interested to read out your antiferromagnetic order. And also here, the PT symmetry of the antiferromagnet allows you this electrically, actually even optically, but I show it only to you electrically, that at least at higher order magnetotransport, namely the second order magnetotransport, you can have terms which are odd under time reversal, so they change sign, like anomalous Hall effect, for example, when you change the magnetization direction, but they are second order. Yeah, and so the way to measure might be not so straightforward. You have somehow to disturb your system and then to see how something you disturb reacts in order to measure this higher order magnetotransport effect, but it's possible. And it has been first shown actually in copper manganese arsenide by Joerg. The one is actually working still on those things, as you can see. What he showed at the time was when you can switch with the spin orbit field, this real antiferromagnetic system, copper manganese arsenide by 180 degrees, by just applying pulses of opposite polarity, you can switch it by 180 degrees forward and backwards. Then using this higher order magnetotransport measurements, you can also read out the corresponding state, yeah, as you can see here. This has recently actually rediscovered, if you want, in manganese bismuth telluride, and came up with two papers recently where they use exactly the same effect. They call it a bit more fancy. It's a quantum metric nonlinear Hall effect. Again, this Hall effect related to the fact that you change the sign if you change the magnetic order parameter, or if you reverse the magnetic order parameter, the L vector. And both of those, this manganese bismuth telluride, grown as a multi-layer stack, it's also a PT symmetric system. Okay, so we said we want to have a brain, a real brain, and we want to do an artificial network. So we can also say we have a real antiferromagnet with a PT symmetry, and we can do an artificial antiferromagnet with a PT symmetry. And here you see the most simple device of artificial antiferromagnet. A synthetic antiferromagnet, where sublattice A is just one ferromagnetic layer, sublattice B is another ferromagnetic layer, and both of them are coupled via exchange coupling, which is simply the RKKY interaction. Well, you see the difference, obviously. Your RKKY interaction is a relatively weak exchange interaction. So the coupling strength between the two sublattices is compared to real antiferromagnets typically much weaker. But the symmetry, at least, is the same, because you can see you have two, say, heavy metal layers, non-magnetic layers, corresponding, for example, to those gold atoms. And you have the two sublattices A and B, and the inversion symmetry at this interface, which is broken, is also broken here, but it's exactly the other way around. Yeah, and therefore now again very similar to the real antiferromagnets. If you send a current, thanks to the spin Hall effect in the platinum, you also generate spin accumulation now at the interface of a staggered direction. Yeah, and the upper one generates your spin pointing to the y, and the lower one pointing your spin pointing to the minus y, and they interact then, of course, via spin transfer torque or spin orbit torque with the local magnetizations of the sublattice 1 or sublattice 2, or say ferromagnetic layer 1 and ferromagnetic layer 2. Okay. If you just look in the system, very simple system, you can see if you just do an anomalous Hall effect measurement, now really in the first harmonic linear response, you can see there when you apply more than 300 millitesla, you are in Z direction. This is easy axis antiferromagnet, so the easy axis along the Z direction out of plane. If you apply a field which is stronger than this 300 millitesla, then you polarize both layers. You overcome this RKKY interaction in one direction along the field. However, at around zero magnetic field, you are in an antiferromagnetic state, which might be fully polarized, but which may also contains antiferromagnetic domains. Now, in principle, you can't really distinguish by a linear response those two states if you are in a antiferromagnetic fully polarized states or in a multi-domain states, or if this fully polarized states, antiferromagnetic fully polarized states has the opposite orientation. All this will be invisible to you in first harmonics. However, if you now use this spin orbit torque writing with a first very strong negative reset pulse, you polarize the whole system, say to one antiferromagnetic state, fully polarized, and you write and you read what you will see. You do it 10 times, by the way. You always set the system to do a little bit of statistics. You see that you actually find a very reproducible way of writing intermediate states, which you now not read out with the first linear response, but with the second response, which you can do by a simple second harmonic measurements. And as you can see, every point was actually is just the arrow bars here is out of the fact that you do the experiments 10 times, always from a fully polarized states. You can see it's extremely reproducible, right? It's very different from what you usually would expect in ferromagnetic systems, where your information is based on actually the position of domain walls, because this is a fact, because what you actually measure here is the ratio between antiferromagnetic domains up and antiferromagnetic domains down, right? So this is a kind of analog memory, if you want, where the information is stored as a ratio of the antiferromagnetic reverse domains, and the writing is done by spin orbit torque driven antiferromagnetic domain wall motion. Right, just to show you that really the effect of this dipolar coupling is the relevant reason why we are in such a high reproducible experiment, I'll show you this micromagnetic simulation, which simulates spin orbit torque driven domain wall motion with very similar parameters, or the same parameters as we figured out from these antiferromagnetic systems. Here we just first consider only one layer having a platinum layer on top. So a ferromagnetic system, if you want, and our antiferromagnetic system containing two layers, right? And if you now look what happens in such a ferromagnetic film, the left one, what we introduced here is one pinning center. This is this little red cross here. And this one pinning center is just done by enhancing the local anisotropy in this area there to make it very difficult to reverse the magnetization at this point. So a domain wall driven by a current will not be able to overcome this cross. But if you now apply a current, you see what is happening. Actually, your system breaks into striped domains. And the reason is for nothing but the magnetic stray field, which generates this striped domain structure. So domains, neighboring domains influencing other neighboring domains. And well, there is no other friction implemented in this system. So there is no anisotropy variations otherwise. We've done other simulation that is also taken into account, but just to show you the effect is, so what happens if you switch now off your current pulse, your system eventually relaxes in the lowest energy state, and lowest energy states means also the domain walls have the shortest length, because the domain wall is it's a cost of energy, right? But the domain wall energy, so you get a minimization of the length. And this is a result. Eventually, your system collapses back to a state which looks actually not so different from the original state, like you haven't applied any pulse. The simple reason here is that you really have the effect of the long-range Limag field, which makes also in this system where you don't have any other friction than this single pinning center here, that you have a 50-50 domain configuration. This is a system with periodic boundary conditions, so that the effect from boundaries don't play a role. So if you look in the SAF system, where the same simulation is done with just two of those layers, but being antiferromagnetically coupled via RKKY interaction, you see that actually the domains don't care about each other. They come very close. The only thing when they start caring is when they feel the exchange from the rotation of the other ferromagnetic domains. That's why you see those kind of, the shape here. So these domains come very close to each other. They don't eventually disappear. They don't right? And what you can see, the only effect of this is actually here the pinning centers. Stray field doesn't play a role. And as a result, if you relax the system, again, you have the reduction of the domain wall length, and you go back to a system which has the minimized domain walls, and therefore, it looks like this, but you can see the pinning center indeed is here a pinning center. Our domain wall stays exactly at this particular pinning centers. So if you would reproduce your experiment at room temperature, where you also have thermal fluctuations, of course, the striped domains would look always different. However, in this case, we would always come in principle to exactly the same domain configuration. That's why this higher reproducibility of our synthetic antiferromagnetic memory. Okay, let's come now to the second part of my talk. But before I do this, maybe if there are questions, I'm happy to answer them now. Or if not, I also can just wait until the whole talk is over. So the next thing, it's about this current-driven antiferromagnetic oscillator. Well, if you think about ferromagnetic spin torque oscillator or spin oscillator, spin orbit torque oscillator, usually people describe it with a kind of macro spin picture, where you have various terms, a precessional term around an effective field, a damping term, and then the current implements, or the spin transfer torque implements by a damping-like spin transfer term, which can actually act together in the same direction like the damping torque, or against it, can become an anti-damping like torque. And then you have a field-like spin transfer torque, which acts effectively like an applied magnetic field. And the whole idea of these oscillators actually can be described very simple. If this damping-like spin transfer torque acts actually with the damping torque which you have inside your system because of dissipation, then you actually damp it even stronger, your system, and you don't get at all oscillation. But if this damping torque is actually compensated by the anti-damping torque, then it's possible to have your magnetization processing at a constant orbit. And so this is the base of many realization of spin orbit torque oscillators or spin transfer oscillators. The first one shown here is a kind of nanopillar oscillator where the spin Hall effect generates your spin accumulation at the interface or a spin current which then gets absorbed in one of the layer of this GMR device, which is a free layer, and starts processing. As you can see, only at one current direction, at negative current direction in this case, you can see a peak appearing in those measurements here. And this peak at the opposite current polarity is not visible because then you are in the damping regime. The same has been shown in nanogap oscillators or in nanoconstriction oscillators. And those nanoconstriction oscillators are very nice because they're in a sense very simple to fabricate because you actually can pattern just a small constriction. The fact that then if you send a current to such a structure, the current density is very high here, and correspondingly, all the effects we are just talking about are becoming very strong here. So you will have a localized excitation of your magnetic order here. And this can be then figured out by, for example, if you have a magnetization which is processing periodically, of course, various parameter change or transport parameters like anisotropic magnetic resistance will change periodically. And if you have also a periodically changing current, this would come up like a DC signal, a kind of rectification signal, and this you can easily experimentally measure. But now, antiferromagnetic spin torque oscillator, maybe also spin orbit torque oscillator, you don't care. But the theoretical concepts here described here are as follows: that you have somehow a polarizing system, a spin polarizer, like a spin injector, and you inject a spin to your antiferromagnetic system, to the two sublattices, which then react with this spin polarization. This also can be described in a relatively straightforward way. What's interesting, that antiferromagnets typically have certain critical points. That's, for example, one point. This is, I will say, these are points which are defined by the strength of the exchange interaction, but also you have, like in the ferromagnet, also magnetic anisotropies, so magnetic anisotropy energies. And if you just overcome such a magnetic anisotropy barrier, where you can actually, with an external field, for example, you can, by simply a Zeeman gain of your two sublattices, when you apply a sufficiently strong magnetic field, you might get a little bit of a tilt of the two sublattices, and then the Zeeman energy you gain may overcome the anisotropy barrier. This particular point is called the spin flop field. Flop means you can rotate your antiferromagnetic order by, say, 90 degrees. It will align the Néel vector then perpendicular to the applied field, because the small magnetic moment you excite, you just get because of the tilt of these two antiferromagnetically coupled magnetization orientations. This will align towards the magnetic field. And at this particular field, you can actually get in a regime where you see chaotic behavior of those spin orbit or spin transfer torque oscillator, antiferromagnetic spin transfer torque oscillators. And this is something very particular in antiferromagnets, which you don't have, for example, in ferromagnets. And especially for neuromorphic computing, those kind of systems where you have a stochastic behavior or chaotic behavior might be of quite big interest. So again, what you have here now is a non-staggered spin injection. So we go away from our PT symmetry, but we have synthetic antiferromagnet, so we are flexible. So we can now use, for example, two other heavy metal systems in a way that our heavy metal from the top and the heavy metal from the bottom, they have just the opposite spin Hall angles, meaning the spin accumulation at the two sides are the same, because in one case you get the spin accumulation from the top, in the other one you get it from the bottom. Okay, so same spin orientation like here in our proposal, where the spin polarizer is now sending a spin current or spin polarized current to our sublattices, both for sublattice A and sublattice B, the same spin polarization. And we do it very simple. We make a system which has an easy plane anisotropy. So the magnetization lies now in the plane. And why we did this? And then we do a little constriction out of such a system so that we have a high current density here, such as I explained before, that we get, if possible, spin or magnetization or magnetic order oscillation exactly at this particular point. Well, okay. If you have such an easy in-plane magnetic system with a magnetic anisotropy, which is easy plane magnetic anisotropy, of course, if you apply a magnetic field, you don't have to overcome a barrier because there is no anisotropy barrier in the plane. So immediately your two magnetic moments will rotate perpendicular to the applied magnetic field. So the L vector is perpendicular to the applied magnetic field, but you generate now, depending on the strength of this magnetic field, a small net moment. Yeah? And you can excite now the system with a magnetic field or an effective magnetic field, spin orbit field, for example. And you will have, you can generate, if you are lucky, antiferromagnetic resonance. There are two modes in this system. You have an acoustic mode. There, this magnetic moment you actually generate by the tilt starts precessing around the axis of the applied magnetic field, a little bit like a ferromagnet if you want. Yeah. And then you have an optical mode where this magnetic moment here is actually changing, summing up is like M1 and plus M2. The two, if you just make the vector sum, you will figure out that in this mode, actually there is a magnetic moment which then oscillates at the precession frequency along this y-axis, in a sense that actually you transfer during this optical excitation energy from the exchange energy into the anisotropy energy on a periodic way. This gives you this optical mode. And this is very simple physics, very long known from Kittel, actually showing that you have this optical mode which behaves with the magnetic field in a way that the frequency reduces going down if you increase the applied magnetic field. And the acoustic mode is just linearly increasing with the applied magnetic field. So this is a very simple system. And if it's simple, then it's always nice to show if you can indeed use new physics, like trying to excite it with spin orbit torque. And this is what we did. We now use not a real magnetic field, but we use our spin accumulation, which periodically changes at the interface, since we send a radio frequency current at a frequency that we actually resonate with these two modes, which I just showed you. And there is some work done in ferromagnets a lot. This technique is used to call spin orbit driven ferromagnetic resonance and ferromagnetic systems. Here's one example where the spin orbit field can be used to excite the precession of the, in this case, magnetization around an effective magnetic field. And then the rectification, because of the changing transport properties like AMR, or in our case, we would have a kind of GMR if you want also, because they tilt to each other, these magnetizations, will cause you a variation, a periodical variation of the resistance. You get a delta R if you want. And this delta R, which periodically changes at the same frequency that the current, gives you, if you have a sinus omega t times a sinus omega t, gives you a sinus square omega t. And this is a constant if you want. So this gives you a DC voltage, which you can easily measure by just using a bias T, where you send into a high frequency signal and you take out the low frequency or zero frequency component as a voltage, which then tells you something about the amplitude of the precession. Is there. So if you are at resonance, usually this comes up as a peak, as a Lorentzian in this measurement. And now the thing is that the system is so clean and the field you can apply in whatever direction you want. So when you apply the field along 0 degree, you only excite actually the acoustic mode. And if you apply your magnetic field along 90 degrees, you only excite the optical mode. And this you see here, you see this black line has a peak at this particular field position where we are in resonance at, if we excite at 8 gigahertz with the acoustic mode, right? And we have to go up to half a Tesla in order to excite the optical mode, simply because the optical mode at zero frequency is so much higher than 8 gigahertz. As I just showed you before, optical mode decreases the frequency. So we can measure the optical mode. But you see something else which is a bit strange. You see this behavior that you have a difference. Now at this particular field of about a half a Tesla, we are another critical field, the so-called spin-flip field. Then we destroy the RKKY interaction, and both of our magnetizations are parallel. But you see then this kind of linear increase here stops. And what we actually see here is the so-called anomalous Nernst effect. Because what we do by applying a field in the plane, as I said, we tilt the magnetization. And when sending a current through the structure, we generate also heat. And this heat is actually distributed unequally in a way that mostly is going actually down in your substrate, in your waveform. And you get a heat current perpendicular to the plane. And this combined with a magnetization which is in the plane, in particular in a direction 90 degrees means you are perpendicular to the direction of your contacts. You have just the anomalous Nernst geometry. And this effect, what you see here, is just the anomalous Nernst effect. Okay, it's an artifact, but we see nicely our resonance peaks. And if you apply 45 degrees, you see both the optical modes and the acoustic modes. And you can do a frequency dependency of these measurements. And it fits very well to this very simple Kittel theory of an in-plane, easy-plane antiferromagnetic system. You see the optical mode and you see the acoustic mode, and distinction is simply by applying fields in different directions. So we can excite ferromagnetic resonance or antiferromagnetic resonance in our system. We can distinguish the two modes. This is already quite nice. So then we actually got the great help from our collaborators in Munich, a group of Christian Bach. And so what he offered us was actually using scanning time-resolved Moog system, where you can measure the polar Moog effect. So if you have a precession here, then you will be able to measure the out-of-plane component at this precession. And when we apply this particular field and excite with only 4 gigahertz, we excite actually at an angle of 0 degree, where we would expect the acoustic mode, a very localized state. You can see here the precession takes place, or the excitation takes place in the constriction. Outside, the Kerr amplitude is effectively 0. Now, if you rotate our magnetic field 90 degrees to it, the effect is gone, because here in this symmetry, we don't anymore excite the acoustic mode. It would be ready for the optical mode, but the frequency for the optical mode is much too low, so nothing to see. So what we have is actually a localized mode. And what you may know from the spin-orbit torque oscillators or spin transfer torque oscillators, it's actually you need those localized modes, which eventually develop out self-oscillations. So effectively, you don't need any more RF excitation, and you start processing the system without any excitation. Okay. Yeah. Next thing, what happens actually if we don't apply a magnetic field at all? So a ferromagnetic resonance would be in this case a bit difficult to do, but antiferromagnetic not, because we could in principle excite the optical mode, right? If we would be able to have the high frequency excitation in our system, or we could still generate an acoustic mode if there is a small in-plane magnetic anisotropy. And indeed, in our system, we do have also an in-plane magnetic anisotropy, which I was not mentioning in the beginning to make it more simple. But yes, there is also an in-plane magnetic anisotropy. So what we can do, we can excite it actually as well now at 0 magnetic field, and we excite most probably the acoustic mode here. And what we see is now a very complex structure, because you have at 0 magnetic field antiferromagnetic domains present. And these antiferromagnetic domains seem to be those structures because this time-resolved PMOC experiment allows you also to look to the phase of the precession. So what is the phase difference between the precession of those two areas? And this phase difference is exactly 180 degrees. So in effect, you have an L vector precession here of your system, which shows you, because they precess out of phase by pi, one is going up, the other is just going down at the same time, you can identify antiferromagnetic domains. That they are really antiferromagnetic domains, you can show with another simple experiment, where you now apply a current pulse through the structure. And a current pulse, as I explained before, you can use in order to move antiferromagnetic domain balls. So this is now a different color scheme. The domain structure after you have applied a pulse, say a positive pulse from left to right. And now you apply a pulse again from right to left. You see your domains have totally changed. The red one became the dominant one, and somehow a small blue domain is still in the center pinned. And then you send the current pulse again in the opposite direction. And interestingly, again, this extremely high reproducibility, you get the same domain structure back as you had previously, as you had the first positive pulse applied. So again, you can modify your antiferromagnetic domain structure, and you can identify this with this time-resolved PMOC measurements. Okay, good. Let's go now towards antiferromagnetic self-oscillations. And this idea, as I said in the beginning, is very similar like what's done in the ferromagnets, in a sense that your damping, which is wire damping-like torque, can act in both ways. It can actually keep an oscillation running, and you have a precession, or it can actually interact, it can overlay to the damping-like torque, and it's actually damping the precession. And this you would have always have exactly opposite current. So if you change the current sign, in one case it's a damping torque, in the other case it's an anti-damping torque. And this is now what will be the effect of a current on a mode which is already there. So we look to the acoustic mode here, right? You see it at both magnetic fields, here at negative magnetic field, here at positive magnetic field. You see the opposite sign of those features. The reason for this is that the precession, helicity, if you want, the sense of precession, is exactly opposite for the opposite magnetic fields. And now if you apply a current, say a positive current at negative field, you enhance this peak. On the other hand, if you apply a negative current, you decrease this peak and it disappears. And the other way, same thing. If you apply now at a positive field a negative current, you will see it actually enhances the peak, the acoustic mode. And if you apply a negative current, it decreases the acoustic mode. So yes, we have actually an anti-damping or damping-like torque due to our spin orbit, spin accumulation at this interface. And therefore, there might be a possibility that we indeed see self-oscillation. Now, we can also do another experiment, which somehow shows us this dependency on current direction. And this is Brinell light scattering, where we here show you only the data from the Stoke peak appearing as a result of the excitation of this magnonic mode at three different current applied. One case zero current. We just see our Stoke peak at 0 milliampere. And then if we apply a positive current, the amplitude remains relatively equal, but shifts to lower frequencies. We think this is due to heating. But if you apply now a negative current, a DC current, you see this huge enhancement of the peak. Again, the shift to lower frequency also of this compared to the zero current yeah, is probably to do simply Joule heating, because the current density in this constriction is quite high. And if we do it at the opposite field orientation, we see exactly the opposite effect, right? So now the positive current is enhancing the peak and the negative current is reducing the peak. So the same thing what we've seen in our, say, spin orbit torque rectification measurement, electrically measurement, we can also see in principle in the Brillouin light scattering experiment. So anti-damping torque is present, and it actually promotes or it reduces the precessional modes, the Magnum modes. Okay, so what about now if we only apply a DC current? So if you only apply a DC current, if you do again micromagnetic modeling of such a structure, where we have a constriction, and this is only considering that the current density here becomes very high, of the order of 10 to the 12 ampere per meter square. We use data which are actually corresponding to our experiments, what we are doing. So we have relatively high intense current densities. There is also a small effect on magnetic field you generate. It's of the order of a few Oersteds. But it's a DC, because it's a DC current, it's also DC Oersted, and it's not really relevant for any excitation we do here. Maybe except that we may guide spin waves because of this local acting Oersted field. And this is what the simulation tells us. Indeed, at a certain current density, you start actually getting self-oscillation here, which then where the energy is actually going out via spin waves, leaving these nanoconstrictions to the outside. And here we just see the effect during a few snapshots at particular times. We use exactly the same parameter as we have in our experiments and our experimental system. So let's try now the real experiment with the nanoconstriction out of our substructure. But before this, maybe just looking also a little bit to try to analyze the data, which you can see here, because the precession is not simple in this constriction. This is just taking an area in the center of this constriction and looking to the trajectory of the local magnetizations of sublattice A and sublattice B. So it's very chaotic, because in a sense, if you do now a power spectrum, or looking what actually are the peaks with respect to the frequency, you will get actually a lot of very narrow self-oscillating modes. Yeah, so it's quite a complex system. And so this is probably something which we would expect in the experiment as well. Well, let's do the experiment. And the experiment we did so far is we actually don't set exactly zero field, but we actually sweep a little bit around the zero field, just in order to generate a homogeneous domain structure, and also maybe to be able to address those various resonant peaks. Because in our experiment, we actually apply only one frequency, here say at 8 gigahertz. Yeah? And if we just apply a small amplitude RF current, you see nothing, right? In the range where we sweep from 50 to minus 50 millitesla, there is no effect. But as soon as we apply a current, a DC current for the structure, suddenly you pop up a lot of very sharp, with respect to the magnetic field here, but anyway, close to each other lying resonances, which are pointing interestingly all in one orientation. And if you now apply the opposite current, you see also now a whole bench of very sharp resonances, which have changed their sign. And this change of sign is actually most probably the fact that the guys are precessing, because they are driven by the spin orbit torque. This torque changes orientation when you reduce from plus to a minus current. We just change the orientation, and therefore the rectification effect, which is what we measure here, is changing its sign. So this is indeed quite a strong indication that what we see are indeed self-oscillation. Now, if we just pick one such a peak out and look now what happens if we change the current, if you enhance the current, you see that there is nothing at low current or at opposite polarized current. But as soon as we overcome a certain threshold, suddenly such a peak pops out. And this is true for a small positive and the corresponding small negative field. So this kind of threshold behavior is another strong indication that our system, what we see, or these peaks are due to self-oscillation. Okay, with this I'm coming actually to the end of my talk. What I showed you here is antiferromagnets used for devices, if you want, very applied talk, using spin-orbit torque, which is can be in real antiferromagnets as well as in synthetic antiferromagnets, be done in a way that you can drive domain walls, in particular in PT-symmetric antiferromagnets. Here we've shown this non-volatile analog memory. The information here, if you want, the analog information is encoded as a ratio between the reversed antiferromagnetic domains. And in principle, the position of a domain wall, if you have only two antiferromagnetic domains, and the writing is done via the spin-orbit torque-driven antiferromagnetic domain wall motion. We believe that the high reproducibility, which we see, is because of this missing of long-range dipolar interaction in antiferromagnets. And the fact that we have a PT-symmetric antiferromagnet allows us to identify the ratio between these two reversed antiferromagnetic domains with a nonlinear magnetotransport measure. This is usually a small effect, a second-order effect only, but in principle, you can also think about a very simple implementation of such a substructure in a TMR device, for example, where you have the reference layer being just having a stable magnetization, and your antiferromagnetic domain wall, which defines the analog state, is the layer which is actually the one you write in an analog way. So you can, in principle, also use the signal, I believe, for having a large output, similar to what you have now in conventional spintronics devices. So maybe a useful device. And then I showed you antiferromagnetic spin-orbit torque oscillators based on also synthetic antiferromagnetic multilayer systems. There we have identified antiferromagnetic resonance driven by spin-orbit torque. Could identify an optical mode and acoustic mode. We could show you localized states, which are really processing, and you excite them only in the constriction. The TR, the time-resolved Moog experiments, could be also used to see actually processing domains, antiferromagnetic domains, which are processing out of phase, if you want, and that's why you can identify them. And you can move them around by currents reproducibly. And finally, we have, I think, quite strong experimental evidence for spin-orbit-driven induced self-oscillation, which are quite complex. You have a lot of modes, as you can see here. This is our simulation, but from the experiments, also here, we see a lot of those small spikes which are coming up, which depend on the current density in a way that you have to overcome a threshold in order to excite those modes. So thank you very much for your attention, and I'm happy to ask questions.
Great. Thank you very much, Joerg. A great talk and lots of results. So we start with Sergey. Sergey, can you please unmute yourself and ask a question, please?
Yeah. Thanks for interesting talk. Really excited to see the results. I have two technical questions. Both of them are connected with optical observation. Was this the sensitivity of Moog, and I guess BLS the same, just to see the magnetization precession of the one layer, or were you able to see the total magnetization precession of both layers? And this is the first question, and probably I ask immediately the second question. Can you explain why in the BLS signal you have a peak at frequency 16 gigahertz, although you excite at 8 gigahertz, where the doubling of frequency comes from? Thanks.
Okay, thank you very much. So the first question, I'm actually not the specialist in the TR mode. You should ask Christian Back or his postdocs or students. But I think these layers are extremely thin. So what you see is actually the signal from both layers, despite maybe the upper lying ferromagnetic layer, which is only a few nanometers thick, gives maybe still a larger contribution. So what you see effectively is the difference to this. But during the oscillation, you have a small magnetic moment, right? This both in the optical and also in the acoustic modes, you have a net magnetization, which you induce by applying this magnetic field. And this net magnetization is precessing as well. In one case, you change in the optical mode, which we probably don't excite in those experiments when doing the TR mode experiments. It will be, in principle, a time-varying magnitude of the magnetization which changes. In the acoustic modes, is actually the precessing magnetization around the field, which then also has a periodic out-of-plane component, which you probably see. And this is, I think, it gives you the signal. So, the experimental setup is such that you have a given repetition frequency of a femtosecond laser, and you can actually measure all frequencies. If you take, if you say, okay, this repetition frequency is say 80 megahertz, and every at the higher harmonics of this, you'll be actually able to identify a signal. So, since this 80 megahertz is a relatively small frequency, well, it's a low frequency. It actually enables you to measure very well, quite a lot of points if you want. So the second question, it was related to why we see the peak coming up at 16 gigahertz, despite the excitation was only 8 gigahertz. But actually here we don't do any excitation. The experiment is done like this, that we have the system without any RF excitation. We apply only a DC current, yes, and this DC current then thermally excites modes, and this mode is actually seen as your Stoke or anti-Stoke sidebands, and then the effect of adding an additional DC current to this normally only thermally excited system, you can see that you would reduce or you enhance this this mode. So you don't have, I think the mode we excite there at this particular field which is applied, I don't know if it's written here, sorry, is probably at 16 gigahertz. So it's an eigenmode of the system which is thermally excited and which is then enhanced or reduced with spin-orbit torque.
So you are saying that the 16 gigahertz and 8 gigahertz is just occasional.
When we do the FMR, when we do the spin-orbit antiferromagnetic resonance measurement, there we apply a given RF current, which has a given frequency. For example, often we use 8 gigahertz. For this micro BLS measurement, we don't apply any RF signal. We just excite a mode which is thermally excited, yeah, because we use also, I mean, there's a laser focusing on this constriction which heats up the sample, yeah, and then when we are adding an additional current, so this turns out to be at 16 gigahertz. Here the field is written at 250 millitesla. You find an excitation mode of this particular device at 16 gigahertz, right? And then if you apply an additional current, either with positive or with negative sign, you enhance the signal or you reduce the signal, telling me, in my interpretation, only that you effectively your anti-damping torque via spin-orbit coupling via this heavy metal layers from top and from the bottom will either give you a damping contribution or anti-damping contribution.
Okay, thanks. This is just coincidence. Okay, thanks.
Yeah, it's just coincidence, exactly. Yeah.
Perfect. Shushan, can you please unmute yourself and ask your question, please?
Yeah, thank you. Thank you for your talk, Prof. And I have a question about technically about the TR mode. So when you try to inject your current with a DC current, then I think in the TR mode measurement, you will make a quite large thermal effect. Then I think then your current density will be limited to a certain value. So my question is about how can you inject a high current density and which matches with your device structure? Like if your dimension is too small, then the TR mode cannot scan dot by dot because the laser spot is large enough, which can cover almost your whole device. Then you need, and maybe so your device dimension should be limited by the laser spot. So that's my question.
Okay, so maybe I go to a picture where I can see here, for example, see the result of a TR mode measurement. And so we apply, in this case, a radio frequency signal, which excites the oscillation, and the TR mode measurements is time correlated to it, right? So the measurement points and the laser pulses and the frequency of your current, they are correlated. That's why it's possible to measure it, phase stabilized. Now the laser spot is, I think, in this system, I'm again not the specialist of it, but I mean, it's probably of the order of a half a micrometer. I think they use blue light or so, or greenish light. So it's really, and it's also stabilized with respect to possible vibrations. So you always readjust in principle this TR mode measurement to the same position. Of course, our constriction here, you can see, is much smaller. It's of the order of about, say, 170, 200 nanometer. So the signal which comes from there is, of course, averaged. However, you still be able to resolve it. In this, I mean, these measurements just show you this, right? You can resolve it, and the resolution is of the order, as you can see here, so half a micrometer, I would say. The current density itself, as you're totally correct, is limited by the actually thickness of your constriction. So typically, you can apply current densities of the order of 10 to the 7 up to 10 to the 7 ampere per centimeter square. So depending on how thick your sample is and how wide your constriction is, you can adjust the current. However, this current is still enough to excite also for those modes here the domains, that even in this wider domains where the excitation is much smaller, simply because current density is much smaller, you see actually the precision of these things. And in addition to this, we apply current pulses. Again, we are limited to this fact that our constriction is narrow, but we can apply current pulses which are able to move domain walls. Yeah. And domain wall motion in this system is possible at relatively low current densities. That's why we can even move the domain walls in this system where the actual current density is relatively low in the wider areas as well. As you can see, this blue domain starts actually moving in this reddish inside and gets repulsed outside when you send the current pulse of opposite polarity. Yeah,
I see. So my understanding is that only when the current density reaches to a certain level at the narrow gap, so we can excite the self oscillation. If the current density is not enough, then it cannot excite this self oscillation.
I mean, the effective current densities where we excite self oscillations, maybe it's written here. Well, we think we excite self-oscillations. So those are simulations, by the way. There we apply effective currents of the order of 10 to the 8 ampere per centimeter square, 10 to the 7 to the 10 to the 8 in this range, very much like we do in the experiment as well. And here, this is a half a milliampere. So it's of the order of 10 to the 7 ampere per centimeter square. I cannot tell you exactly because I don't know how wide the constriction of this particular device was. But this is an area where we can see then the self-oscillation. And when doing the current dependency, as you can see here, they pick up the self-oscillation, what we think are self-oscillation. They come up at a given current density, which is, I think, 400 microampere. So we are still in a range where we can actually, we don't burn our device. So I think we can apply it typically in those devices up to milliampere, 1.5 milliampere currents, and it will still survive. So it's, yeah.
Yeah, thank you. Then I have one last question about this current pulse and the laser pulse. I mean, for TMOG, it's actually a sampling technique. So how can we, it's like a sampling oscilloscope. Every time we need some trigger to make it synchronized.
Yeah.
So how can this current pulse to be synchronized with this?
So the current pulses are
not,
sorry, the current pulses are not synchronized. So but in this experiment, you apply just a current pulse and then you do a synchronized measurements, but it's not synchronized with the current pulse. There was only a single current pulse, which changed from this to this, for example. And then we do a measurement of a RF signal, a current, which is indeed synchronized to the TMOG measurement. So this frequency of this, say, 8 gigahertz or 4 gigahertz in this is a multiple of the frequency of your laser repetition rate. Yeah, so the femtosecond. But you seem to be a specialist, I think, so you know maybe much better than I do. But this frequency of the repetition rate is a multiple of the frequency of the RF excitation. That's why you can measure it. So you don't measure every period, but you measure time delayed, right? You can make a time shift between them at every, say, 1600 period or every 2000 period, right? Depending on what kind of frequency you use, you measure that, you leave the system processing and then you measure every 16,000 period plus 1/2 of the period or plus 3/4 of a period. And then you can scan over the phase.
Oh, I see. Thank you. Maybe I need some time to understand this timeline. Thank you. Thank you for your explanation.
You're welcome.
Hey, excellent. And then Pradeep Kumar, just so for the other ones that wrote a comment that the 16 gigahertz BLS mode is in the eigen mode of 250 megahertz.
Very good. So he's the one who did the measurement.
I think that's all the questions for today, and then we're kind of a bit out of time now, so I'm going to turn off here this streaming.